In the previous video, we did introduce the curl, also called the rotation, for vector fields. This is given by the cross product between the nabla operator and the vector field. And similar to the cross product, which is multiplication with the perpendicular parts of two vectors, we have the very simplified description that the curl is the derivative in the direction perpendicular to the flow. However, just as for the divergence, it's a bit more complicated, which we'll see in the following example. We are basically going to show the same examples as we did for the divergence in the previous video. But this time with the curl inside a circle of radius 1, and we will use polar or cylindrical coordinates to do it. As the curl is a vector, we will define the constant curl omega 0 z hat inside the circle and 0 curl outside. Similar to the divergence, the curl will get a different expression in this coordinate system. This time, we will assume divergence-free flow and that the flow far away is 0. We know from previous video that the divergence gave the flow in the radial direction, hence 0 divergence means that the flow in the radial direction is 0. This gives the same differential equation as for the divergence example, hence I'll give a very quick solution. Multiply with the radius and integrate both sides. The integral over the derivative is the function, and the other side is the integral over a polynomial. Then divide by r. Inside the circle, c has to be 0, otherwise we get the infinity at r equals 0, which is unphysical. Outside the circle, we only have the term with the integration constant c. The integration constant is determined by assuming that the flow velocity has to be the same for both expressions at r equals 1. And we basically get the same expression as for the divergence case, but this time the velocity is in the tangential direction. When we look at the velocity field, we see that the particles rotate around the center, hence the name rotation. In this case, it's very obvious that we have a curl, as we can see the particles rotating. But it will not always be this easy, and we need a better visual technique to determine if we have rotation or not. Assume that we create a cross of a solid material, which means that the flow cannot pass through it. If we place the cross floating in the fluid, will the cross be turning? If it rotates, we have rotation or curl. When it's placed in the center, it clearly rotates. The next question is, how fast? Call the rotational speed of the cross capital omega, which means that any point on the cross moves with velocity omega r. As the flow cannot pass through the cross, it has to rotate with the same flow velocity. Hence, we can identify omega as omega 0 over 2, meaning that the cross has a rotational speed of the curl divided by 2. If we place another cross inside the circle, but not in the center, it will both rotate and travel around the circle. As it rotates around its own axis, we have a curl here. The rotation speed is the same as for the cross in the center. If we place one cross outside the circle though, this would only be traveling around the circle. It would not rotate around its own axis, as the flow is irrotational, or as curl 0 here. Note, we are assuming that the cross is small compared to the radius of the circle it moves in. This particular cross will also only detect curl in the z direction, as it has its axis of rotation in this direction. To find the rotation in the x direction, place the axis of rotation of the cross in this direction instead. I also want to introduce the concept of circulation here. This part requires that you know about line integrals to follow. Define a closed curve somewhere in the flow. Here we have made the curve a circle with a radius larger than 1. The circulation is what we get when we calculate the line integral of the velocity around this curve. In our case, the flow velocity is parallel to the curve, and the line element ds is r d phi in polar coordinates. Next, insert expression for the velocity at the radius larger than 1. R will cancel. As there's no phi dependence in the expression, the integral will simply be a multiplication with the length of the interval. The 2 will cancel, and our circulation is simply omega 0 times pi. Later in this course, we will see that this also can be calculated using Stokes' theorem. Our next example will be a pipe, similar to what we did for the divergence in the previous video. This time, place the curl minus omega 0 z hat in the red region in the center of the pipe, and let the curl be 0 outside. We can now calculate the flow velocity. Note that it's only the dvx dy term that gives a contribution. The rest of the terms are 0. Remove the minus sign. As both expressions are in the z direction, we can remove the direction and integrate both sides. The left-hand side is just Vx. And the right-hand side will be omega 0 y plus the integration constant c. This will give a velocity in the x direction looking something like this. We have a linear increase in velocity in the curl region, constant velocity outside this region. Now, call the height of the curl region delta y and assume that delta y times omega 0 is a constant. This means that the total curl is constant, and by changing delta y, we only change how large area we distributed on. With this assumption, if we change the value of delta y, we get a different velocity gradient in the curl region. But the difference in velocity between under the curl region and above the region stays the same, even when delta y goes to 0. This is what we would call a vortex sheet in fluid mechanics. It's mainly a mathematical approximation for a jump in flow velocity. Let's continue with talking a bit more about different relationships one can find for the curl, the gradient, and the variance. To make things easier to write, I will first introduce the vorticity omega as the curl of E. The first relationship is A dot the vector gradient, which is the directional derivative in the direction of A multiplied by the length of A. This equals the transpose of the vector gradient dot A. This is a direct consequence of that the vector gradient can be considered as a dyadic product. Use the associative property of the dyadic product. As these are scalars, we can change the order. Use the associative property again. And use that if B and C change position, we get the transpose. Hence, we have shown the property for the dyadic product, and therefore it works for the vector gradient as well. Now, I want to use this to evaluate what happens if I take the difference between the transpose of the vector gradient and the vector gradient dot A. Start by typing out the matrices. Tensor subtraction can be performed element by element. We can first note that all diagonal elements will be 0. These two are minus omega z and omega z respectively. These two are omega y and minus omega y respectively. And these are minus omega x and omega x. Now we can perform the matrix multiplication. Start with the first row. Continue with the second row. And the third row. The final vector is omega cross A. Let omega and A swap places. And replace omega with the curl of V. We can distribute A and use our expression for the transpose matrix dot A. And rearrange. This is the relationship between if you take the grad V dot A and A dot grad V. The next relationship is the gradient of a dot product. It basically follows the traditional product rule. But we have to set the gradient first in both cases. If we use the equation above, we can also write it as where we only use our directional derivative and the curl. We can also write that the gradient of A cross B is the gradient of A cross B minus the gradient of B cross A. The curl of a scalar f times the vector A is the gradient of f cross A minus the curl of A times f. And finally, we have the expression for the curl of a cross product. I have skipped the derivation for several of them, but it is relatively straightforward to prove them by evaluating both sides component by component. When you use these in the future, you will likely just look them up in a table of equations. Let's continue and talk about the connection between the curl and the gradient. The first question we will ask is if it's possible to write the velocity as the gradient of some function phi. Assume that we have a rotating flow v equals a constant k in a tangential direction phi hat, which is this field. Let us write the expression for the gradient. Once again, it will be different from the Cartesian coordinate case. It is only the tangential direction that will be of interest here, as this is where the flow is. We can drop the unit vector and multiply with r. Integrate both sides. Left hand side is just phi. Right hand side is the integral of a constant. For this illustration, we can drop the integration constant as we only care about the gradient of phi. Then let us plot the value of phi. There is one major issue with this figure. I encourage you to pause the video and try to figure it out yourself. The problem is the following. If we use Cartesian coordinates, each set of x and y coordinates should have only one value for phi. And we know that if we add 2 pi in the angle in cylindrical coordinates, we have the same x and y. This means that in cylindrical coordinates, adding 2 pi should give the same function value as before. This is clearly not the case here, as we have a larger value each time we add 2 pi. Hence, this is not a valid function. The conclusion is that it's not possible to write a given velocity field as a gradient when it is rotating or as curl. To be a bit more mathematical, start by looking into what happens if you take the partial derivative with respect to x of the phi y. Apply the definition of the partial derivative to the phi dy. The limit delta y goes to 0 will not affect the x derivative and can be placed outside. Now, we can apply the x derivative to each term. Use the definition of the partial derivative again. And again. We can move the limit when x goes to 0 outside as well. As these have a common denominator, these terms can swap places. Now we can distribute the limit when delta y goes to 0. Note that this is the partial derivative with respect to y. And this is also the partial derivative with respect to y, but at position x plus delta x. Move the partial derivative outside the parenthesis and place the limit inside. Finally, identify these as the partial derivative with respect to x. The final result states that taking the partial derivative with respect to x of the phi dy is the same as taking the partial derivative with respect to y of the phi dx. Or we can say that it does not matter in which order you take the partial derivatives, the result will be the same. This does assume that the derivatives are sufficiently continuous though. With this result, we can mathematically check what happens if we take the curl of a gradient. Apply our result to these terms by changing the order of differentiation. Now we can see that every single term will cancel and the result is a zero vector. As the curl of a gradient always is zero, it is impossible to write v as grad phi if v has curl. While I will skip the proof, this works in the other direction as well. If the curl is zero, it is possible to write v as the gradient of phi, as long as the domain is simply connected. A vector field that can be written as the gradient of a scalar is called a conservative vector field. Now, why do we need the condition that the domain is simply connected? Consider our previous field with the curl inside a circle. This is a rotating field, and we know that it cannot be written as a gradient, as you have curl in the center. But what if we delete the center from the domain? The field is still rotating, which means that we cannot write it as a gradient. But the rotation is zero everywhere inside the domain. The issue is that the domain is not simply connected, as the circle is missing. And for these domains, it is possible to construct fields where the curl is hidden in the missing regions. Therefore, we need the simply connected condition to ensure that this does not happen. It may still be possible to write the simply connected domain as a gradient, but we cannot be sure it works. A similar result to that the curl of a gradient is zero is that the divergence of a rotation also strictly is zero. If you want to prove it, do it in the same way as we did for the curl of the gradient. This will give a similar result that if the divergence is zero, we can write the vector field as the curl of psi. Psi is called the vector potential. In fluid mechanics, this is called a stream function. In electromagnetism, one often talks about the magnetic vector potential A. Finally, for any vector field, we can always write it as a combination of the gradient of one function phi and the curl of another function psi. Here, phi will give the divergence of the field and psi will give the curl. I'm not going to go any deeper into this here, but the main conclusion from the Helmholtz decomposition is that the divergence and the curl can be decoupled from each other. We did see this effect when we studied the circle in the beginning of the video. The divergence gives the radial velocity and the curl the tangential velocity. We can change one without affecting the other. Next up, we're going to talk about the divergence of a gradient. Start by writing the expression for the gradient of phi, then the expression for the gradient operator, and perform the dot product. It is common to write the second order derivative as d2 phi dx squared. Repeat for the other two. This is what we call the Laplacian. It can either be written by the delta symbol or by writing nabla squared. This is the most common version of the second order derivative for scalar functions in multivariable calculus. Let us visualize this with an example. Start by plotting the function phi, here represented by Gaussian distribution. Next, plot the gradient of phi as a vector plot. The Laplacian phi will be the divergence of this vector field. Similar to the ordinary second order derivative represented curvature, the Laplacian will also represent the curvature when we add the contributions from all directions. A classical example where this is used is the diffusion equation, which states that the change in value for phi will be some constant k multiplied by the Laplacian. By looking at the figure, we can therefore expect that phi will decrease fastest in the center. When we animate the solution, we can also see that this is the case. At the end, where there is no more curvature, the Laplacian goes to zero. To mention some more examples where we have the Laplacian, we have the wave equation. The easiest example is probably the Laplace equation, which states that the Laplacian is zero. Another common one is Poisson's equation, where the Laplacian equals a function. These are examples you may come in contact with later, as they will appear in physics in many courses. Finally, if we apply the Laplacian operator to a vector, in Cartesian coordinates, it is the same as applying it to each coordinate separately. Once again, it only works for Cartesian coordinates though, otherwise it's more complicated. The last equation I will mention is that the curl of V is the gradient of the divergence of V minus the Laplacian of V. This follows the same pattern as the back-cab rule we learned for the vector triple product. It's important to know that the gradient of the divergence is different from the Laplacian. Hence, when you work with vectors, be extra careful and remember that the Laplacian is the divergence of the gradient. That's all for this video. Thank you.